Okay, welcome to the course Software Testing, and this is the third week of the course. And today we're going to talk about, or in a moment we're going to talk about, we also need to address the assignments and such things. So for the schedule for today is that we're going to look at the assignment first, and then we're going to talk about test effort assessment, and perhaps after that, if we have time, then we do a bit of coding. So let's start by talking about the assignments. So now you should have completed assignment 1, part 1, and if you did see green in the end of the screen and it said that the assignment was completed, then you're fine. And if you failed to reach this before the deadline, then I want you to do an extra bonus assignment, which is pretty much to tell me how you and I, or we as the ones responsible for the course or the university, could have done differently so that you would have been able to complete. Weird things are happening. Okay, so that you would have been able to complete this assignment before the deadline. It could be things that I should have done differently, like being better with my communication with you. Perhaps you should have received an early warning or whatever. Perhaps you misinterpreted the instructions, so there were too many instructions or too few instructions or whatever. Or perhaps there weren't enough days between you starting the course and the deadline of the assignment, and you've been working the whole time or whatever. Or you probably, most of the students who did not finish this assignment before the deadline probably had some reasons for that. And I'm not really interested in the reasons. I mean, you can tell me the reasons if you need to, but that's not what I'm after. So despite your reasons, how could you have succeeded before the deadline? And I mean, in some cases, I mean, if you have been vomiting for 3 weeks now, then okay, or been at the hospital for 3 weeks or whatever, then you could not do this. But I mean, then the deadline could probably be moved. Okay, so assignment 1 is completed, and you should have, you should know if you have succeeded in that or not. So. And everyone who has seen green on Friday at 16:15 should be approved of that assignment right now. So I'm not going to enter these grades into Ladok until I know who's going to do the optional part of assignment 1. Because I need to grade you, and the optional grade is for high grades. So now the mandatory E grade assignments is done, and you have the option of doing assignment 1 part 2 for higher grades. And this assignment is can be done, or at least the programming part of this assignment can be done in a group of maximum of 2 students. If there are groups here and you want to work with someone else and you don't know anybody in the course, use Slack to find someone to work with. I mean, there are probably other students who are also looking for someone to work with. So, and this is also true for assignment 2, which we're going to talk about in a few moments, that where you can work at least part of the assignment in groups. Okay, so assignment 1, part 2 is about X-unit testing. And you cannot really fail the assignment, so to speak, because in order to start this assignment, you need to have completed assignment 1, part 1 before the deadline. And you can only upgrade your grade from this assignment. So it's recommended. I think it's mandatory that you need to finish the first part first. In this part, you really need to read the instructions carefully, and because there is a specific way of working here, so don't just start going off working and then think that you can read the assignments later. In the instructions later, you really need to understand how to do this in order to succeed. And the reason for that is that you're going to work in a test-driven development manner, like I talked about on the last lecture. So I recommend everyone to watch that lecture first. I wrote at least 20 commits. I'm thinking that most students who have done good in this assignment does around 10 times more commits, or something like that. So TDD was that you're going to write a test that fails. You're going to also mark this piece of code that you did during red by producing a commit in your Git repository. So you're going to make a commit with the word red in the commit message, and then you're going to change the implementation so the test suite succeed, a minimal change, and you should mark that commit with green. And then you do a refactoring, so you rewrite code or the test suite, and then you mark that commit with refactor. And when we examine this assignment, we want you to be able to show in your commit history on Git that you've actually worked this way. Therefore, this is the evidence that you've been working in a TDD manner. And we also want you to try to use coverage tools. So you're supposed to use coverage measurements, and you can mark these coverage measurements. So you save the report or take a screenshot of the report or whatever, and then you add this into Git under a coverage commit with a covered commit message. Okay, so it could be a text file like a coverage report or a screenshot image. And there are a couple of requirements for the project, and these are sort of minimal requirements. And what I really want students who are going to get a higher grade in this course to know is that they should have tried unit testing of many different things. So it's all about learning to test in different things. Yeah. So we want, for instance, these classes to have dependencies, so that you need to test things in isolation, so that mocking becomes something that is useful and needed for you. And in order to get mocking working, you need dependency injection, and you need to isolate dependencies, and you should be able to detect bugs and pinpoint the exact location. The accuracy of the tests should be good, so that it pinpoint to the position of the bugs. And we also have a bit of weird requirement here that somewhere in the code you're supposed to, not only at startup, create objects with the new operator. So somewhere inside the method you create objects, and perhaps you add those to some internal data structure, perhaps you return these, whatever, but you're going to need to test that code. And this brings some extra, you need to think about how you're going to be able to do this and also isolate dependencies, which is not super hard and not super simple, but factories are involved. I think it's a good idea to communicate in Slack, preferably in the open channel while you're working with this. I also want the project to have some kind of UI, some kind of user interface. Could be console-based, could be a web page, could be some kind of user interface, graphical user interface. Actually, more or less recommend these two, because I've been working with TDD and console application and working with TDD and web applications. I have not really done this. And perhaps this part is something that you sort of wait and not do in the beginning. So start easy, work your way to more complex things during this assignment. And in the end, you're going to be examined, and we have individual examinations. And we want to see different things during this application. We want to ask you different questions. And I mean, please discuss these questions also in Slack if you want to. I think it's a good thing to discuss these. There are probably things that are like hidden behind some of these questions, and not every question has an easy answer. Not every question has a just one answer. And yeah, so I think these are good questions for discussion. And if you're thinking of doing this good, think of these questions as like essay questions on a written exam. So think, how would I explain this to someone, and what are the different approaches. And you need to, booking procedure will be announced on the web page. I'm not logged in here, but if you're logged in, you should be able to see a link, and you should be able to book yourself during the examination week. So if you open that link, there is a spreadsheet with a lot of different places where you can book your examination. And there is possibility to do the examination online in Kalmar with me, or in Växjö. So I mean, you can do the examination on site on any of these sites or online. If you do it online, you need to have a webcam. You also need to have a headset, and you need to have a stable internet connection during that assigned time slot. So the examinations week is going to be a pretty hectic week for me and some of the tutor instructors who are also involved in this. So we might not be able to like answer other questions during that time as quick as we used to do. And please check the deadlines for when you need to be able to have booked yourself into this form. And yeah. Okay, that was assignment 1, part 2. And then we have assignment 2. Since assignment 1 is sort of done for some of you, you should look at assignment 2. And assignment 2 is not a small task, it's a pretty large task. In this assignment, you're going to be given a system. So you're going to be given a program and also a scenario. And you're going to see if this program is fit for this scenario. So you're going to plan, and you're going to conduct, and you're going to report a testing of this system. So it's your responsibility as testers to find out if this system is good for this scenario, if it's going to be recommended for this scenario or not. And you need to devise a test strategy. That means you need to think about, okay, given the resources that we have in our group, because you can do this as a group, how can we do the best job as testers? So you may work in a group from 1 student, so you can do this alone, to up to 4 students. If you're 4 students, it means that you're supposed to do 4 times the work. So you have much more hours than if you're just 1 student. There are some goals, and there are some theory. And then we have the scenario, and you're also given the source code and requirements for an application. And here is usually some confusion, because students are trying out, checking these requirements, checking the software, and they say that, okay, I don't know anything about web servers, but I'm spoiling a bit here because it's a web server. And that is the first thing. So in order to test a web server, you need to find out how web servers are supposed to work. So you need domain knowledge in order to be a good tester. We talked about this during Basics of Testing, the first lecture. In order to test something, you need domain knowledge. So yes, you need to read up a bit on web servers. I mean, most of you have been interacting with web servers all your life. So you've been browsing web pages, and that is sort of what a web server provides, like web pages. So a basic requirement could be that we're going to be able to see a web page at some point. But it's not certain that the web server is working, and I can spoil also to say that there are things that are not working in this web server. I mean, it's, yeah. And you're going to write the test strategy, and that means the overall, we've not really stepped into the strategy part of lectures yet. So if you're starting now, you're sort of doing things a bit in the wild. But I mean, the last year's lectures are out there, so you can watch these and yeah, be able to do this assignment anyway. And I mean, the deadlines are not really super tight. You're going to think of, okay, I'm going to focus, I mean, strategy is the focus of your testing. So we're going to focus, for instance, on manual test cases, or we're going to focus on automated tests or something like that, and the reason for that. And then you're going to plan your work. So, and a plan is who is going to do what when. So I'm going to write some manual test case for these requirements, and this is going to be done by Tuesday or whatever. And then you need some manual test cases for the application. And then when you have these things, I mean, you have your strategy, you have your plan, then you're going to execute the plan. I mean, do what the plan says. And from that testing, you're going to get results. So for instance, perhaps the web server does not provide the web page that it's supposed to do. Perhaps it's providing something else instead, and that means a failure, or perhaps the web server provides what you expect it to provide, and that is a success. So in the end, you get your different test efforts and results from these. And I think in the end of the report, I think it's a good thing to think back of this scenario and say that given the results we have, we recommend that you're not going to use this software, or something like that. So you come up with some kind of conclusion. This is going to be a couple of different files. I mean, you're going to create a couple of PDF files, and you're going to zip this and put them in a zip archive. And yeah, there are different rules for these. And then you're going to upload this into the peer review system. And the peer review system is a system where you upload a document, and everyone who uploads the exact same zip archive is going to be placed as a group. So it's very important that one of the group members zip these different PDFs files and then distributes this zip file to the other students. So you cannot zip the files. Everyone in the group does it by itself. It's not going to work, because then you're going to look like you're 4 different groups. So you enter the peer review system, and you can upload your file there. And when the files are uploaded and the deadline for uploading has passed, then you're able to do reviews of other students' work. And then the group work is done. So you're no longer working in a group, you're doing the task 2 on your own. So you're going to look at other people's documents, and you're going to review these on 3 different factors. They are called clarity, which means language, format, disposition, and completeness. Is everything that should be in this document that we asked for, is it in the documents? So I mean, I've written questions here in order to guide you through that review process. And then thirdly, content. So given the, so you've already done this testing yourself, so you know that, okay, we were in a group of 2 people, we should be able to do this much work. And if you're looking at a group and they say that they are 4 people and they've done less than you, perhaps they've not done a good work, right? Perhaps that group should have done more work, more testing, given the efforts they had. Of course, groups can run into trouble, but I mean, getting the software to start and stuff like that should not take more than a couple of hours, or at least this group should have asked for help during tutoring if they had that kind of trouble. So I mean, content part is more or less the ambition and test effort of the other group. And then you're gonna receive reviews from other students. And I've changed the system this year, so you're not gonna see the scores that other students put on your document, but you're only gonna see the text parts. The reason for that is simple. I mean, we don't want revenge scoring or stuff like that. We really want you to focus on the task of writing reviews and then also receiving these reviews, and then think of, did the reviewer do a good job? Did they find the problems that you know about in your effort? Yeah. And then finally, there is a scheme for grading, and most of this is gonna be hidden for you, but one way of affecting your grade is writing more reviews. So in order to have the highest grade, you need 4 peer reviews that are all considered really good. You can have more reviews than 4, and the topmost, the best one, is gonna count. So if you have like done 5 reviews and 3 of these are marked as excellent, and 2 reviews are good, then you're probably gonna get a C. Oh no, this one. I mean, so, but the rules should be clear, and I mean, you can always ask about this. Okay, that was the assignments that is pretty much starting right now. So let's continue with the lecture part of the lecture. Unless anyone has any questions that came into mind. Okay, so test effort assessment. And part of the test effort assessment is going to be included in both assignment 1.2 and assignment 2. So this can be good to know in order to start these other things. So test effort assessment is, how do we know that the testers of this project that we're looking at are doing a good job? So it's a quality measure, really. So we want to know if someone did a good job, can we trust this product, can we trust whatever. And in order to dive into this problem, I mean, we can have different viewpoints of this. If you're doing manual testing, perhaps have different test assessments. So the focus of this lecture is going to be on X unit, like J unit, test suites. How do we assess them? And we're going to take a look at one such test suite for a project called Yoda Time. So Yoda Time is a Java project, and it's been around for many years. It has 2,139 commits, 6 different branches, 74 different people have been working on this project since it moved to GitHub. I think it was living in other places before that. Yoda Time it's a quality replacement for the Java date and time classes. So you can have like multiple calendar systems, and you have a simple API. There are different requirements, and I mean the requirements of this project is not the important thing here. The important thing, and the thing that we're going to ask ourselves, are: do we trust the code in this project. And one way of finding out if I want to trust this is, can I see if the developers of this project did any testing? Because testing should provide confidence, both for the developer themselves, but also for me as a user. So if I'm going to use their API, I want to know that they did a good job testing. Otherwise, I'm probably not going to trust their code. Right. Okay, so I don't see anything about testing in the documentation. But looking into the source code, and I mean, we do that, we find a test suite. And this is Java, so everything is deep inside folder structure. And then we find, oh, there are some tests. And I mean, there are subfolders here with more tests. I don't know what this is. And more tests. And I think this was the one where I should step back into, and some tests for the convert things. Oh, this looks good. Or at least they had tests, right? And we can, I mean, we could, I think this one, test all, is, it's a test case, and you can see that they're building up test suites, and they add all the other suites. So this is a super test of all the tests. So we could, like, perhaps run these tests in order to find out. And if we run these tests, we find out if the tests succeed or if they fail. And that would give us something. If a lot of their tests fail, then we have a couple of different ways we can think about this. If they fail, either the test is saying that the system is not working, so we should not trust this system. Or the test fails because the test and the system have like parted from each other. So that the test is no longer testing this system, this version of the system, it's testing some old version and is no longer compatible. I mean, that could also be a reason for test failing. If you like change an interface, but you don't update the test suite, then then the test will fail because it's no longer supporting the new interface, and then the test results is going to be worth nothing. So running the test suites is a good idea, and that's going to give us a lot of information. Okay, so if all these tests succeed, then I feel a bit better about using this system, right? But, and I've just scrolled through here, it's impossible for you probably to understand how big this project is. But if we take a look at, actually I don't know this source code very well, but let's step into the source code. We see that now I'm not in the test suites anymore, I'm in the system. And we can see that, oh, there are a lot of classes here. And there are subfolders with even more classes. And it's just a feeling I get, but, and I didn't really count, but perhaps there are more classes here than there are tests. If that's the case, if they're only testing some of their classes, then perhaps we cannot trust the system because only some parts of the system is under test. So in order to find out that, we need some kind of way of assessing their unit testing suite. So that is the goal of this lecture, more or less. So, and a way of thinking of this is to ask, is these tests good enough? And we call that adequate. This is a reference to the old book that is not available, which is a problem in this course. But hopefully I'm going to show you some links here that you can take a look at. So what could be an adequate test? So the way that I think of tests is that each test is a constraint on the solution space. So the big gray area here, the big gray cloud here, is all possible solutions to a problem. So we were testing some numeric strings last lecture, right? And we had some social security number class. So I could have written my code in many different ways in order to implement this. I could have a social security number that were just a text string, and it didn't have any validation on if there are numbers, or we could support dashes in between these numbers, because Swedish social security numbers are sometimes written like 6 numbers and then a dash, and then 4 numbers. We could support like 12 numbers, social security numbers. We could introduce bugs. We could write the code in many different ways. So the gray cloud is the set of all possible solutions. Some of these solutions are better than other solutions, the correct ones. And correctness, we defined that during the first lecture, was that for any input, the system provides the correct output according to the specification. That was the definition of correctness. So the green cloud in the middle is a part of all possible solutions, the correct ones. Those have no bugs whatsoever. And I mean, a lot of these all possible solutions is going to have problems. Like if you start the program, it's going to crash directly, like student projects. There can be compiler errors, there could be bugs that are so severe that this system is unusable. So the green area around the correct one is systems that are partial correct. For at least some inputs, these systems works. Probably the code that I wrote during the last lecture did work for some inputs, and probably did have some. I didn't have validation, for instance, for the Loon algorithm. So social security number has a digit, which is a control digit, which should give you some certainty that when you enter a social security number and you press the wrong digit somewhere and you make a simple error, then you can detect that problem. So that is called the Loon algorithm, and we did not implement that. So our solution was partially correct. So we're in the light green area here. And the way that I think of tests is that they are like putting lines through this solution space, and every solution that is sort of on this side of the line is now excluded. So if I have one test case, I can like remove faulty solutions, and I keep all the correct ones, because we should, with a test case, correct solutions should pass the test case, unless the test case is faulty. So it's like a dividing limit, removing all these faulty solutions and some of the partially incorrect solutions also, and keeping all the correct ones. So it's a constraint. And you can add more test cases, and the more test cases, the more certain you are that your system is going to work as it should. And both of these test cases are good test cases because they exclude different types of problematic solutions or faulty solutions. This one could be a good test also. It's excluding a lot of faulty solutions, but you can see that the sort of precision of this test to exclude also in partial correct solutions is not that good. So it's not as good a test as the other ones, but together they provide pretty good testing. This test case that I've written as a dotted line could be good unless we had this test before. So some tests, even if they remove all this gray area here, this test is removing less than this other test, so it's not as good as that one. So apparently some tests are better than other tests. And if you have this test that I'm pointing at now and then another one that is the same, then you can remove one of these because you don't need both of them. Okay. So now we know a little bit about, okay, what testing is. Testing is constraints on this solution space. And here we have two axes. On the left to right axis, the horizontal axis, we have the requirement input domain. And then on the top to bottom axis, or the vertical axis, we have requirement, output, or behavior. So, I mean, the correct way of behaving with a certain input. So I put a green dot in the origo of this diagram, and that means that for the input 0, so to speak, it's supposed to output a 0. So now we have one test for a specific function here. And one test could be good enough if we have an adequacy criteria that says that that is what we say is good enough. So in order to find out, is it good enough to have one test, we need to have some kind of way, some way of thinking of or calculating how many tests we need. So this criteria is that a test T for a program PR is considered adequate if for each requirement R in R, there is at least one test case in T that tests the correctness of P with respect to R. I wouldn't write it like that. What it means is really, if you have a requirement, you need a test for each requirement. So given this adequacy criteria, this single test case would be good enough or adequate. But because we have one requirement, so to speak, and we add one test case. I mean, sometimes this is the way that you do things. And if it's a very simple method, perhaps we only call it once. We only have one test for it. Or in many cases, we don't write that simple code. We write more complex code. So perhaps we should add another test case. So you can see the second green dot here. And both of these test cases are succeeding. So now we inputted like a bit higher on the x-axis, means maybe 5 or something like that. And we got the correct output, perhaps a 5. And if I have two test cases like this, perhaps this could be enough if the implementation is some kind of linear system. So with two test cases, I don't know if you see it, but I see a line through them. So human brain is set up to like see patterns in things, and if the pattern or the function that we're implementing is a line or a bit more complex than things that we were talking about before, then perhaps two test cases is enough. And I mean, two test cases here sounds fine, but what if the actual thing that, or the requirement that we're implementing is something like that? Then these two test cases are no longer enough. Then we need to add more tests. So now I've added down here a green dot, and suddenly, or maybe if I have these three test cases and they succeed, all of them, perhaps our testing is good enough. So the more complex the system, the more tests we want. we could also have these test adequacy criteria that says this is what we mean with good enough. There can be different types of these, and we're going to talk about these in a moment. Okay, so here is another test adequacy criteria. It's called path coverage. And it says that a test T for a program PR, and with test here, I mean, maybe you should think of this as a suite of tests and not just one test. A test T for program PR is considered adequate if each path in P is traversed at least once. And you see the code up in the right corner or above me. And you can see that, okay, it has an if statement. If x is larger than 2, then we throw an exception. After that, we have a do-while loop. And within the while loop, we increment x with 1. And we do that until x is less, or as long as x is less than 2. And after that, we return x. So if we take a look at, or we graph this code as a graph, we can see that from position 1, or the if statement here, it creates two different paths, one for the true and one for the false. And if I end up in state 2 here, then we will throw an exception. So you're not gonna, we're exiting from this state. And if the if statement returns false, we're gonna step into 3, which was the innermost part of the do while loop, and we're gonna increment x. And then we're gonna move down to the while test statement. And if this is true, we're gonna step up to 3 again and increment x again. And if it's false, we're gonna step down to the return statement. So there are different paths for this. So the test adequacy criteria that I presented earlier, called path coverage, says that each white arrow in this image here must be covered once. So we need a test case that goes from 1 to 2, and then we have that part covered. And then we need another test case that goes from 1 to 3 to 4 to 5. That could be a good test case. And then we need a third test case because this path is not yet covered. So we need a test case that goes from 1 to 3 to 4 to 3 to 4 to 5. And actually, the middle test case, which was 1, 3, 4, 5, can be removed because it was included in the 1, 3, 4, 3, 4, 5 test case, right? So some test cases are better than others, right? And given a certain test adequacy criteria, we might want to reduce our test suite so that we have fewer test cases, they are faster to run, and and okay, let's be careful here. There are other cases where we want all 3 test cases here. We actually might want a 4th one or a 5th one perhaps. Okay, so I think that we can take a 10-minute breather and then we're back with more testing. Okay, welcome back to software testing, and this lecture we're talking about adequate tests and how to evaluate our test suites. And we were talking about this different types of test adequacy measurements, and I've given you a couple of examples. The latest was the path coverage, so we try to find each path through this graph, which is a representation of the code, and if all the arrows have been covered, then we say that, okay, this is adequate. I've also said that we can have multiple tests that cover the same paths, and for a certain adequacy statement like this one, you can perhaps remove some of these tests and still have adequate path coverage. That said, I also hinted that we might want to keep some of the paths, and I'm going to talk about another test adequacy measurement called loop coverage. So loop coverage is not written here really, but it says that all the loops in our programs, the do while or the for loops or the while loops or whatever loop we have in our programming language, all of these must be covered 0 times. That means that we should go through this one 1, 3, 4, 5. So we don't really, a do while loop cannot really be run 0 times, but a normal while loop could be run 0 times. So you're not really entering into the loop because of the condition. And loop coverage also says that you should run the loop 1 time, so that would be 1, 3, 4, 3, 4, 5. And loop coverage also says that you should run the loop multiple times. So for that, you also need a test case that runs 1, 3, 4, 3, 4, 3, 4, 5. Together, these test cases give loop coverage. And you will have 100% loop coverage through your source code if you do this for every loop that you have in your program, which might not be possible, and I'm going to show that on a later slide. So, okay, now we know that coverage is a thing and adequacy, so it would be quite good to be able to measure this, perhaps on the test suite that we're evaluating. So how can coverage be known, and how does coverage tools work? And I've entered a link to instrumentation, and instrumentation is a way of monitor a product's performance, and you let's do a practical example. So let's say that we have this code here. So here we have some code where you connect to a database. And basically to connect to a database, you call the connect method on a SQL adapter, some kind of object. In order to find out if this method was called during test at all, we could enter a log message inside the code. So we instrument this code, we add new lines into this code. In this case, we say that, okay, when we run this log, then we add do connect to a log somewhere. And afterwards, if we want to know if do connect was called during tests, then we just check the log and search for do connect. Then we know that this method was called. So sometimes you might want to also check if do connect was, if we were returning from do connect. So did we ever step out of this method? So you can add another log line after each line. If you have many lines of code in a method, then you could put this in between each line of code. Some lines of code are longer and does more than others. So some lines of code are actually producing multiple statements And you might want to instrument the code so that these logs are instrumented between each statement in order to get what we call statement coverage. So statement coverage says that each statement in your program, so for instance, every assignment, every if statement, every for loop, every system out, every call to a method was at some point during test executed. So it was run during tests, and that way we can find out statement coverage. Statement coverage can look like this. So this is JUnit and Java again, and a piece of code. Actually, I think this might be from assignment 2. Perhaps. I'm not super certain. But you can see that some parts are green, and those lines are called during the tests. And some points are red, and those are not run during test. So by looking at statement coverage, we can find out which part of our program should be tested more. For instance, the close method that closes the socket should be called during test. Okay. And write file would be a good thing to call that one. And we can see that write file has a while loop inside it. We also, if we want statement coverage, want the out.write byte array 0 bytes red line to be executed. And therefore we need to make sure that when we call write file during our tests, we reach into that one. So we need to produce input in such a way that we reach into that one. When I showed this one, I just want to say that there is a reason for these not to be called also. So I mean, there might be reasons where we don't want to call some parts of the code during tests, because perhaps this code does things. If you have a payment system, and like Swish or bank transaction or Visa or something like that, if you have a payment system and when you call an API, you're actually paying money, perhaps you don't want to run that code during test because you're going to pay for that. So in these cases where payment systems are involved, there usually are test API we can connect to instead. But yeah, just to give you a reason. And I think my point of this slide would be that, okay, sockets are closed. Perhaps we don't want to test that because it's messy, and writing files might also be messy during tests. Okay, but the same graph as the old one, and by now you've heard of two different types of coverage, three different types of coverage perhaps. We had sort of the component coverage was the first thing we mentioned. Yeah, this one is more or less component coverage. So if you have a requirement, that should be in this with at least one test. Then you heard about path coverage, which said that each path for this should be reached. And then I told you something about losing track. Statement coverage, yeah. And the first types of coverage that I'm presenting here, component, class, method, block, and statement, are different levels of coverage. So component coverage would be say that if I have like 3 different components in my program, if I run a test for each and every of these, so some code in these components are called during test, then I'm done. Then that's it. Class coverage could be each class in my system should have a test. If I have one test for each class, then done. Method coverage could be that each method in each class in my system should be called at least once. Then I might miss out stuff, like if I only have 1, 2, that path covered, I'm missing out all of these, but I still have at least called this method once, right? So going down this chain increases the test effort and also increases our confidence that we're doing the right thing. Block coverage means that each block of code is run at least once, which means that a block of code is statements that always run together. So if you have a couple of variables that are assigned, like a equals 2, b equals 3, c equals 4. If you have those lines after each other in a piece of code, they are, if you run the first one, you're always going to run the third one, right? So they're in the same basic block. If you have an if statement, that is splitting the code into different paths. So number 2 is not in the same basic block as number 3. Okay, so you can block coverage, and you can also have statement coverage. And statement coverage words that each statement in the program is run. Already told you about loop coverage and path coverage. And there are different types of coverage. And since we don't have a course literature covering this, no pun intended, I've included this link. So code coverage analysis, and here is a link where you can read, and I want you to read about different types of coverage. And it tells you about statement coverage, tells you about decision coverage, condition coverage, multiple condition coverage, and stuff like that. Modified condition decision coverage. So here is an adequacy statement for these. So let's just read this one and see if we understand anything of this. Every point of entry and exit in the program has been invoked at least once. That means that if you can start the program, and with program here, we might mean a method. So if I can start the method, we have done that, right? If we have two different ways we can return from this method, I need to take both of these. So if I have two different, then I need to call this method twice with different inputs so that I reach both return statements. Every condition in a decision has taken all possible outcomes at least once. Oh, that's a bit more complex. A decision, you can think of that as an if statement, or the condition in an if statement. So if we say that you have an if statement and that evaluates to true and to false, it must, during test, be evaluated to both of true and false. That is the possible outcomes. But if you have a switch statement, you can have more than true, false, right? You can have different cases. And then, more complex, every decision in the program has taken all possible outcomes at least once. Each condition in a decision have been shown independently affect the decision's outcome. This is a bit more complex, and I recommend you to read the explanation in this file. But if there are multiple things, like multiple booleans that are like boolean expression for this condition, then each part of that must have been evaluated, and each part of that must affect the decision's outcome. A condition is shown independently to affect the decision's outcome by varying just that condition while holding out of, yeah. Okay, so you can see that there are different types of coverage. I think this is pretty much explaining it. So take a look at those. And read that document. It's pretty good at explaining them. There are probably other places also. Okay. Given this and the different types of coverage, now I'm going to tell you about the DC. Perhaps I'm doing a good job testing. But when I mentioned loop coverage, I also mentioned that it's my expression, unreachable coverage, but this is something that I experienced when I tried to do my best testing. This is also a piece of assignment 2 source code, which was a web server. So, and somewhere in the web server, it's handling different HTTP headers. HTTP is the protocol for the web, And there can be different things in these headers, like the user agent, for instance, is keeping track of which browser name you have. The content length is the length in bytes of your HTML document that you're downloading and stuff like that. And I implemented this as an enum, and there are different things in this enum. And somewhere in this code, I'm parsing the actual HTTP message, which is a string that is coming in, the header of that. And I'm splitting it on semicolons, you can see here. And unless I get two different parts, then I know that, okay, this is wrong and stuff like that. Then I step through all the different values in this enum. And I check if the header that I'm looking at is starting with this text. And if it does, then I find a header and say this is a valid header, and then I return a new header with this. Okay, doesn't really matter the details here, except when you're starting on assignment 2, of course. And if I don't find any, I return an unknown header. So let's take a look in the bottom of this screen if I can get this one to disappear. How do I get it to disappear? Yeah, thank you. So in the bottom here, there is a coverage report. And it says that the statement coverage for HTTP header and for header class is 100%. Good job, Daniel. You have covered every statement with at least one test. Good job. The branch coverage of the header class is 100%. But the loop coverage is not 100%. And the reason for that is that this loop here can never go 0 or 1 time, because it will always go multiple times, right? Because I told you that loop coverage was running each loop of the program 0, 1, or multiple times. So since this is only running this code multiple times, because the enum has more than one header, then I can never reach 100% loop coverage with this piece of code. So I have unreachable coverage. I cannot get 100%. I could, if I'm like twisting myself inside out, I could mock the HTTP header class and create a mock class with 0 headers and a mock class with 1 header. But I mean, that would be stupid, because it's not going to affect the quality of my code. It's not going to help me find any bugs, because it's always multiple times. This means that you need to interpret these coverage reports and not just read these and say, okay, you have only 33% loop coverage, pretty bad, while it's actually pretty good in this case. So most metrics are like these. So we try to come up with a number that says how good something is, and it's not that easy to find a good number, because all numbers have problems in it, and measurement problems like this one. I've also found unreachable coverage and part of the code that was really hard to cover. And other things that I had problem with was static void main. I could not run that during test suite or during the tests. I don't know if it changed in later versions of JUnit. Might be that you can run the main method. I could not do that, at least when I wrote this code. I've also found that if I had double checks, so you have one if statement somewhere that is checking the input length or something like that, and then a bit later you have another if statement that is also checking sort of the same thing or the same thing, then of course I'm not going to step into that one. So you can have unreachable code, you can have dead code. So coverage is a good thing, and I think that during assignment 1, part 2, you should run a coverage tool on your code, and you should get a coverage report. Hopefully, if you've done TDD, you will have a really high coverage measurement. My experience from doing this myself is that you're going to be around 100%. Might not always be around 100% because of the story that I told you about the loop coverage. It might not be, you might have unreachable coverage, right? And the same thing goes for you during your assignment 1, part 2. There might be things that cannot be covered. And even if the assignment says 100% coverage, if you have unreachable coverage, that's fine, right? I'm not super strict. But I want you to find these and think of it at least. Okay. Other experiences that I've had is that for more or less the same thing as things might be hard to test, they might also be hard to show coverage for. So if you have like a file system that you're interacting with, a database, an API or a network, then writing tests for this is a bit messier. And also getting coverage of these things might be a bit messier. And there are things like timing issues, state issues. You might need access to some parts of let's talk about access shortly, just so that you know. If I'm communicating with an API, and this communication with the API maybe costs money, and I'm calling methods on someone else's servers, and that costs money. It could be, for instance, that we're other than costing money, it might be security issues. Only people with security clearance may call this API, so that the wrong people don't get access to the wrong kind of information. So if you have this kind of API, maybe you as a tester or you as a developer don't have that kind of access. So you cannot really test this code during tests, really, because only other people have these access keys. There might be configuration problems, there might be hidden dependencies. Most of these things, if you're able to write the code yourself, can be solved by dependency injection and mocking. And I felt pretty frustrated with testing before I found out about mocking. And I usually say that mocking for me brought much joy, because suddenly I could test much more difficult things. Okay, other things that I've run into when coding is, I'm a bit of a nerd, and I like a lot of nerdy things like dinosaurs and electronics and computer games and all them things. Sci-fi and games, whatever. And one of these things are electronics, and I've been doing my fair share of building robots and stuff like that. And some of you might have heard of Arduinos, which is a microcontroller, small computer board, not really credit card size, but a bit bigger than a credit card. And you can attach sensors, and you can attach effectors, motors, different things, and then you program these. And I found out that these are pretty hard to test, because the code that you're writing are only supposed to run on this specific hardware. So if I'm going to test this, I need to have an Arduino. And I might also need the sensors, all the things connected to this with actual wires connected to this one. So having special hardware is a bit problematic. It's like a dependency in our code to something that is hard, that forces me to do. And it's a bit harder to mock this, unless you may run tests of your code in a simulator. So there are ways to do things even with specialized hardware. So most companies that work with hardwares like mobile phones and stuff like that also run code in simulators. So you have like a computer in the computer, virtual computer, which works as an Arduino, and then you have virtual wires, so to speak, so that you can control the environment around this. I'm not really super much gone into that part, but I've done a bit into that. Okay. Other things that also creates a bit hard to show coverage. And coverage was sort of, did we test this enough, right? So if you have a regular expression in your code, then in your code, that regular expression is just a string. And then you run this regular expression engine on this string, and then you find out an output of that. But a regular expression can be pretty complex. So I usually use one of these regular expression tools, and a regular, perhaps we can just regular expression cheat sheet. A regular expression is really a parser for strings. I would like where you have a specific syntax like this. So different characters within brackets matches different parts of strings. So regular expressions are really good when you're like building a web server and want to find out if a header is in there or whatever. And you have different things. So /d matches digits, /big D matches non-digits, /s matches white space characters and stuff like that. So you can match strings. Really good for handling and language queries, checking if something is valid, some string is valid and stuff like that. But a problem with a regular expression is really, it's sort of a programming language in itself. So in order to know if you've tested this regular expression good enough, you would need to create test cases for the different branches in this. So for instance, if you have a regular expression that might match not only one occurrence of a keyword in a string, and it can match multiple occurrences, then you need a test case for 0 occurrences, 1 occurrence, and multiple occurrences, right? But there is no coverage tool that I know of that can handle both Java or PHP or whatever language you're using and regular expression and see that your regular expression needs 3 different test cases. So if you have multiple languages like a regular expression inside of your code, you need to maybe think outside the box. You need another testing strategy for these in order to get a good coverage of that. You might, for instance, need to put these regular expressions in a specific file and then have a test strategy for these. I'm also writing Lua here and scripted, and really this applies to all things that are scripted. And Lua is a programming language for computer games. So you might have a game engine running the game, and then you might have a Lua script for a lot of the content in the game. So if you're playing like a role-playing game in some fantasy world, and your character in the role-playing game is opening a door, and something should happen when you open the door, the house should explode or whatever, then that part is probably scripted as part of the level. And that script could be a Lua script. And if you're testing your, so to speak, Java application and running tests for that, it might really be hard to know if the Lua script is going to be covered, and all parts of that. So when you have multiple languages, you're going to be having a hard time to show coverage. you may show that the Java application or the programming language that you're testing is 100% statement coverage and 100% loop coverage. But it's hard to show that both the Java application and the Lua script is 100% covered. Okay. Related to that is that if we have data-driven code, like when you create an Android application, behind the scenes there is some dependency injection. And so you're really configuring much of your application using XML. But this applies if you're configuring your application using JSON or really complex inputs. You're building up these really complex data structures in your application. So like a level in a computer game might be a map, and each position in the map might be different tiles, and on different tiles there are can be attached monsters, and on monsters there might be attached weapons, and on the weapons there might be a spell attached to that one. So we have a complex data structure capturing the entire game world in this way. Good luck getting 100% coverage and understanding how all of this complex stuff is going to affect your code, because all that is input, right? And the function that you're running this input on should be 100% coverage. But how do you know when you have such complex input? Because the input domain, which was the domain, all the possible inputs, is so super huge and so complex when you have input like JSON or XML. Okay, that said, you might still divide your application into smaller parts, taking care of a part of that input by themselves, and then you can get coverage of these smaller parts. So the solution for some of these problems is also to divide things into smaller parts and test those separately. A big, complex thing is hard to test. Small, easy things are easy to test. Yeah, so I'm probably boring you by now because this is a boring slide. Yes? Yep. Okay, so I get a question when I have multiple languages. If I can have different testing frameworks that test the different languages. Yes, you can have. But most of the time, at least I include the regular expression as part of my Java code. So, but a solution to this would be to like export this regular expression and load that from a file, which I then can test separately. And Lua scripts, of course, you have those in your own file, but it's not always the case that these scripting languages have these testing frameworks, though. Okay, sort of similar is that if you have iterative or recursive function, that means methods that are calling themselves, or methods that are called multiple times, like in a loop. Simulations are typical things like that. Or things that are multi-threaded and are interacting with these threads. It creates so many possible combinations and such complexity in the inputs that it makes it hard to test, and it's hard to know if there is any coverage. I don't know if there is any coverage tool handling recursive functions, like having loop coverage for recursive functions. That a recursive function should have been called 0 times, 1 time, or more times. I might be somewhere, but I don't know about it. Okay, so coverage is good, but there are some backsides to this story also. It's not always easy to show coverage. It's not always that if you show coverage that you are actually given the information that is usable for you. And this next thing is a question that I used to get during assignment 1, part 2. And the question is sort of like this. So I've written this code, and I have tested the public methods, but I also have some private methods. Should I test my private methods or not? And the answer to that is, well, it depends. One way of thinking of this is that if you have a class and it has its public methods, then that class should only be called upon during its public interface. You're not able to call the private methods, you should not call those. So when you're testing this class, you should think like black box testing, another word from the basics of testing. But some interfaces, and with interfaces I mean the public methods of this class, might not be that easy to reach code inside inside the private methods of this class. So we sometimes want to call the private methods separately. And I mean, there are ways of doing this. Some test frameworks allow us to test the private methods. You could change the private methods to protected methods and then inherit from the class that you're testing, and then you open these up in the inherited class. So you create public methods in the inherited class, which calls the protected methods in the, so I mean, there are technical solutions for solving this. But my answer would be like this. If your class is so complex that you need to test the private methods separately, then you should probably split your class into another class which consists of the private parts as public parts, so to speak. And I mean, then you're probably doing too much in this class. So so that would be my answer. Okay. There are parts that might not be susceptible to mocking, like Java console and stuff like that. I think I've mentioned this during the last lecture, right? That not everything can be mocked. Okay. During basics of testing, I also mentioned smoke testing. And smoke testing was tests which we run as large part of the system as possible. And if the system crashes, or if the system never stops to run, or if it uses 100% CPU, or things like that, we call those signs smoke, which means that something is wrong. But normally, smoke tests don't have asserts themselves. And we look for smoke, we see if it crashes. If it crashes, then there is fire. That means that we should do some debugging. You can, for instance, have a test that looks like this. This is the test case, run the system, and you run the system. I mean, this is just fake code, but I mean, you could like execute the entire system, see if it crashes. And you don't have really any asserts here. But what you hope for is that if there's something wrong inside the system, so you have some fault, you have some bug, it should produce or infect the state to an error state, and that should be detected somewhere in some validation code or stuff like that, and that should make the test crash. You can add in-code asserts in your system code in order to do this, or you can throw exceptions if invalid input is like called on your constructor and stuff like that. There are these in-code asserts is a part of something called, should have written it here instead, something by contract, programming by contract I think it's called, or defensive programming. It's actually something called offensive programming or aggressive programming also. So you regularly run methods to check the state that it's not in an error state. So you have code that checks the state of the program to make sure that things that should not be is not. This is called invariance. So if you have a class like let's say that you have a person, and this person has an age, and we say that one invariant could be that age is a number that may not be negative, because we cannot be minus 32 years old or something like that. So as a test in our invariant method of this class, we could check that, or we assert that age is larger or equal to 0. Perhaps we also check that age is less than or equal to 150, because we don't know of any people who are more than 150 years old, or whatever. So all these things that check state, we call those invariants. There are ways of having an invariant method into a class that is run like in the end of all methods, to make sure that if you call a method, you don't change the state into an error state and stuff like that. Oh, it says here, designed by contract, it's called. Defensive programming, dynamic type, so these two concepts are worthwhile to check into if you're working with code that is a bit more sensitive, I think. There is a programming language that is called AFL. I've never been programming it myself, therefore I'm a bit uncertain, that has this built into it. So, okay. Yes, I'm thinking that I'm just pushing things down your throat right now, but we're more or less in the end of the lecture now. But I think before we start with this, we take another 5 minutes breather so that you can think of other things and be more attentive. Okay, so we were talking about how to assess unit test suites, and we were getting to talk about tests without asserts, and we talked about smoke tests, which was more or less run code as large part of the system and see if something crashes. And there is another way of having tests with value without any asserts, which I call complementary negative tests. It's again my definition, so if you search for it, might mean something else to someone else. But in this course, in all cases, we call them complementary negative tests. And this is a test that starts up the system, much like, or not starts up a system. It's a test that only have value together with other tests. So for instance, if you have a lot of these tests like this one over here, where we really are testing that an exception is thrown. You've probably seen this assert expect exception in JUnit, might be called expect exception also in PHP unit, right? Yeah. And in my own framework, it's called assert expect exception or something like that. Assert exception was thrown, I think I'm calling it. This is another way of doing the same thing. So you have a try, and then you call the method that you expect to throw an exception with, given the input. So here we call a new die, and we input null, and that should cause an exception to be thrown, and we should end up in the catch here. That means that what we expect, right? But if we don't end up in the catch and no exception was thrown, then we fail this test with assert fail. So that is a way of doing that. And then if you have a lot of these tests for this constructor, for different ways that this constructor can call an exception, if you have the code inside the constructor that is only throwing the exception, then perhaps all these tests succeed. But so in order to show value, you need a complementary negative test that is working as it should. It's not throwing an exception. It's not really doing anything else than calling a new die with proper input, and that should not throw an exception. So in the end here, it's just calling new die, new random, and we don't have an assert here. Because we don't need that assert, because the asserts are sort of in the other tests. So this test down there is not really valuable without the other tests that are throwing asserts. Not always that this is valid. Often I start up like this and then find out I always need a system under test instance, and this line of code ends up in the setup method. But yeah. Okay, so we talked about different ways of measuring how good a test suite was, right? So we've measured statement coverage, we measured path coverage, loop coverage, whatever. We've seen that these coverage measurements are not always accurate. We can get parts that are not easy to show coverage for, and like that. So now we're going to have another way of thinking about if a test suite is good or not. So, and this has to do with, yes, Adam.
Jag bara undrar, de här testerna, negative tests, är de tysta om de går bra?
Okay, so I get a question if these negative tests are quiet if they go okay. Yes, they are quiet. So there is no assert here. The only way that this should not throw a proper should not throw on a proper argument. The only way that that test could fail is if the code inside that constructor throws an exception, right? If it throws an exception when it shouldn't, then that fails. And that's the benefit of the test, right? Another way of evaluating test suites would be to create faulty versions of the system and see if your test suite captures those. That's the way CS quiz that you used under assignment 1 part 1 is working. So I have a number of fault versions of the system. You have no access to those, but I run your test suites against those and see if your test suite finds the bug by failing a test. I also have a correct version of the system that your test suite should pass. But mutation score is a way of automating this. So you create this faulty version of the system And you do that by seeding the system with artificial defects. We call these mutants. And we check if your test suites find them or not. So we really test the ability of your test suite to differentiate between a correct implementation and mutated implementations. A good test suite is good at finding faulty implementation. And if you remember one of the first slides where I put lines across or called the tests are constraints on the solution space, that was inspired from this. So let's change the system and see if the test suite fetches. There's something called equivalent implementations. There are links down there also that you can check out these systems. So let's consider this test. So should throw exception. The input is 5. We called the system's call method with this 5 input. It should throw an exception. So if it did not throw an exception, we assert fail. And let's take a look at part of the system code inside the call method. If I is above 4, then throw new exception. So this is the system code. That is what we want to test. But right now, we're not really super interested in if this contains a bug or not. We're interested in if the test suite, which consists of one test here, is a good test suite or not. So how good is the test suite over to the left? How good is it at finding problems in this implementation in the right? So if we input 5 into this one, we get an it will be 5. It will throw an exception. So we're going to succeed this, right? Because it's not going to fail, right? Okay, so in order to find out if this is a good test, let's change the implementation into something. Let's mutate it. So let's switch the bigger than operator to a less than operator. That is a mutation. So we create automatically by using perhaps Java Launch or some other tool, in changing that. So we take that code, switch operator to I less than 4. Suddenly, if I run the code on this mutant, I is still 5, so 5 is less than 4. No, it's not, so I'm not going to throw the exception this time. So this test is going to find this mutation, right? Let's create another mutation. If I bigger than or equal to 4. That is also a mutant, right? Suddenly, the implementation or the mutant here is not discovered because 5 is larger or equal to 4, right? It's still larger. So we're going to throw an exception. So this test is not going to find this mutant. A better test, or a complementary test to the one that we have there, would insert a 4 into the system. If I had another test that should not throw an exception, right? If I had that complementary test which calls the suit with a 4, then those two tests together would find this mutant. But the test that I have here does not find it. And finally, okay, let's ignore that image for a while. On the lower end here, you have another mutant. So now I've not only changed the comparison operator, but I've also changed the number to a 5. So this is still a mutant. So let's take a look at it. Okay, we send it a 5. if I is larger, or 5 is larger or equal to 5, it's equal, so we're going to throw an exception. So that is going to be succeeding the test case. But this test case here, can we create this mutant on the lowest mutant, can we create another test case like we did with the mutant above it to identify that this is a mutant? And what should we input? Or how should we write that? So take 5 minutes, think of this. Okay. Anyone found a test case? Complementary test case, perhaps, that can find this? So if I send it a 4, it's not going to throw an exception, right? If I send it a 4, like a complementary test I found before, it's not going to throw an exception because and if I send it to 5, it's going to throw an exception. If I send it to 6, it's going to throw an exception. If I send it to 3, it's not going to throw an exception. But this is actually the same behavior as the system, the topmost one, right? So this system and this mutant are equivalent. They are working for every input. They are working the same, which means that I cannot kill that mutant. I cannot write a test case to improve my test suite that is finding this. So we call this equivalent implementations. And this is the problem with mutation score. So mutation score is you create a lot of these mutants. So now let's consider the image. So each pixel on the right axis of this image is an instruction. And the white lines, so to speak, on each pixel is statement coverage. And the green, oh, it's so bad that it's in the end of, the green and blue and red is output from mutation score. So you create mutants on the instructions on these lines, and then you run your test suite against these. And if your test suite can find these mutants, then it's a green line. If it fails to find these mutants, then it's red or blue. So we can see that for this test suite, now I think it's just red that is the failure. So in this part of the code, I'm unable to find mutants, and over here also I'm also unable to find mutants. But I don't know if the kind of mutants I'm unable to find are equivalent implementations or not. Mutation score is the number of mutants that we find or kill, as we say, compared to the total number of mutants there are. So if there are 3 mutants and I'm able to find 2 of those, then I have 2/3 or 66% mutation score. In this case, if these are the only mutations that there can be, then 66% is very good because the last one was an equivalent mutation. So that should really have been excluded from this. The problem is that it's very hard to know if a mutant is an equivalent implementation or not. If we take a look at people who wrote Java launch, I think, so annoyed by that one. Let's do it like this. So this is Linnaeus University in Saarbrücken, and they created this tool for running mutations against a program called Java Launch, and one of their features is that they produce very few, around 3% equivalent mutations. So for those of you who become interested in this, this might be a fun way of testing your test suite after you've done assignment 1, part 2, if you're working with Java. Or if you want to test the test suite given to you by me in assignment 2, you could try Java Launch on that one. Okay. Another approach to finding out if a test suite is good enough was invented by me, but a year after it was really invented by some other guy. And I called it assert coverage, but he called it checked coverage, but he was first. So, and the idea behind checked coverage is that if I run a piece of code like I do on the right here, and I have a test for that code on the bottom right. So this is the test. I call the do calculate with an input of 1, and then I assert that the actual is 4. So y becomes 1, x becomes 5, and then it prints something. And then we take x minus equals 4, so suddenly x is 4, right? Because it was 5 before, y was 1, so x is. And then we check if y, which was 1, is larger than x, so it's not, right? So we don't step into this, and then we return x, which was 4. So that was the run of this test case. This test case succeeded because the actual was 4 and the expected value was 4. But in this test case, not all lines that were run affected the result of the assert statement. So this line of code, the if statement, so to speak, did not really change what was returned here. The print statement did not change anything. It only printed x, never changed this assert statement, the outcome of that. So this statement over here, the print statement, is not really tested during this test. In order to test the print statement, which is a system console or console log or system out call, in order to test that, we would need another test case that checks the console log or the system out, right? So the checked coverage would be only lines of code that contributed to an assert statement is called covered. So in this case, it would be this line because x gets its value, this line because x is changed, and then this line because x is returned. So for this, this test case only tests these 3 lines, so to speak. It sort of tests this one also, but it's, the way that you calculate this is by something called dynamic slicing. I'm not going to go step into dynamic slicing, but there are tools that can find the dependency of different lines of code. And if you calculate the dependency of these two things, then you find out that it's dependent on this, it's dependent on this, and it's dependent on this. Yeah. I did run checked coverage when I wrote my tool for it, and I want to find out, is this any good or not? Does it give value to anyone? So I created a test suite for some triangles and some vectors, code which I wrote, and then I looked at the test results. And the white, I already told you, was statement coverage, and the yellow here is what I call checked coverage. And you can see that almost for all code, checked coverage is the same as statement coverage. There are some places, like here. You see that you only have white here, but you lack the yellow. And over here, there are some places also where you have white, but you lack the yellow. So there might be places where you have statement coverage. You run the code, you run the print statement, so to speak, but it did not affect the assert. So you should add more tests. I also ran this, using my own tests, because the test was so good, it looked like statement coverage and checked coverage was almost the same. But when I ran this on other test suites, I found out that they ran tests on code that got covered by statement coverage or loop coverage or things like that, that were not really testing anything in that code. So we could have a large part of the code that looks like it's tested, but really you don't have any assert statements for those pieces of code. And I met a former student that was talking about how they use testing at his work. And we were talking on the train, and it was pretty interesting to hear his thoughts on this. And he said that he got to a group and they pretty much solved failing tests by removing the assert statement. And then they committed that as test fixed. That would be like running these two lines of code and then commenting out the equals, assert equals. It's just stupid. They don't fix anything. They only remove the test. Suddenly the test is just a smoke test and really does not have any good idea. So for them, it would be really good to have something like checked coverage. If you want to check into checked coverage, it's David Schuler that you should. Okay, final slide. Now I presented a couple of ways to evaluate your test suites. So you can run coverage measurements, you can run mutation score, and you can run checked coverage. I would say that mutation score and coverage, statement coverage or loop coverage is probably what you should look into. Kent Beck, who wrote the test-driven development book, test-driven development by example book, he says more or less that, well, if you follow the TDD process and you do that good, then you probably don't need to check coverage, because just following the process should give you a very high coverage. And he says that insufficient coverage is a sign of badly designed tests. So if you get this, it's probably because you could not design your test in a good way. I would say that it's a pretty weird statement, really. I mean, yeah. It's like saying, don't do any errors when you're coding, then you don't need to test. Okay. And this was the end of that lecture. So next lecture, we're going to step into system testing, which is more into assignment 2, so to speak. But let's continue the discussion on unit testing in Slack, because a lot of you is supposed to start on assignment 1 part 2. And I want the people who are thinking of doing assignment 1 part 2 to book the examination session. So there is a link on that page for examination, and I want you to book that. There's a deadline for booking, so don't miss that one. Okay, thank you very much.